Stability analysis is quite a complex process. I'll do my best to clearly explain my reasoning and the key points of focus. This video only covers a simple calculation and the basic construction process. The full procedure involves many more technical and detailed steps. If you have any questions or suggestions, please feel free to leave me a comment. Here's my approach to stability testing. First, I take into account that the most important factor related to stability is the center of gravity, CG, as well as the relationship between neutral point, NP, and center of pressure, CP, under the given wing and tail configurations. Once the center of gravity is estimated and set, the rest is mainly related to the wing and tail configurations. So, I'll start making adjustments from that part. Now, what's the relationship between the main wing and the tail? There's actually a practical rule of thumb for this, which is mainly determined by the area of the main wing. In the end, I work backward from the main wing area to arrive at the final stability results. While calculating the area, I also refine the detailed configuration of the wing based on the results, so that the overall stability can be further optimized. I'm still using XFLR5 for the analysis, and I'm basically neglecting the influence of the fuselage. The wing area is most closely related to lift, and lift is directly linked to stall. A microlight needs to have a permit to fly from the CAA, and under UK regulations, its stall speed in the landing configuration is defined as about 35 knots, or 18 meters per second. According to the UK CAA Alpha TADS, the pipistrelle has a VSO of 17.7 meters per second. In the initial model, we can see that the stall speed is around 17.5 meters per second, corresponding to a stall angle of attack of 26 degrees. To convert this initial model to a Class 3 aircraft, we need to further increase the safety margin, allowing the aircraft to maintain a lower speed and a smaller stall angle of attack without stalling. So, what's the solution? Keep the aspect ratio unchanged and slightly increase the wing area. By working backward from the lift equation, the starting area comes out to about 10.1 square meters. Increasing the main wing area S reduces the required CL max, which in turn lowers both the stall speed and stall angle of attack, thereby increasing the safety margin. After running the calculations and tests, the stall speed dropped from 17.5 miles per second to about 14.5 miles per second, while the stall angle of attack decreased from over 20 degrees to around 15 degrees, at the regulatory stall speed of 18 miles per second. This means the aircraft can now maintain lift performance at a smaller angle of attack. At this point, the wing area has increased to approximately 12.276 square meters. When considering wing area, it's not just the stall condition that matters. The takeoff requirements also need to be met. In the end, I take the larger value between the two as the final wing area. The takeoff rotation speed, VR, is roughly 1.3 times the stall speed, and the takeoff lift coefficient is about 85% of the maximum lift coefficient. Considering a maximum takeoff weight of 500 kilograms, we can estimate that the wing area required to meet the takeoff requirement is about 14.071 square meters, so I select the larger of the two calculated wing areas for the main wing. Next, we need to determine the size and position of the horizontal and vertical stabilizers. Here, S is the main wing area, L is the tail arm, that is, the distance from the center of gravity to the aerodynamic center of the tail. B is the wingspan, and CMGC is the mean geometric chord. In light aircraft design, there are some empirical formulas and reference values for these parameters. This gives us the initial tail surface area. Here, the tail arm and the tail area are not fixed values. They are two interdependent parameters. Using empirical formulas is, of course, the most convenient approach. But the most suitable calculation would be to solve it using an optimization algorithm that considers all results in order to find the set of optimal solutions under multiple constraints. I won't go into further detail here. Next, we further optimize the overall wing configuration, checking stability and improving flight performance. After entering the weight data, the center of gravity is located about 31 millimeters from the wing's leading edge. Using the point where Cm-Ho alpha slope approaches zero, the aerodynamic center is found to be roughly 280 millimeters from the wing's leading edge. This gives a static margin of about 18% of the Mach, mean aerodynamic chord, ensuring stability while retaining a certain level of maneuverability. However, in this configuration, the CLCD is not at its peak during stable level flight. This means there's still room to further improve efficiency. Considering the basic performance requirements of a Class 3 aircraft, the main wing uses a straight wing design, without any forward or backward sweep. Straight wings perform better at low speeds and also help reduce manufacturing costs. In the original model, the main wing's incidence angle was about 2.5 degrees. By comparing CLCD values, I reduced the incidence angle to 1 degree. Especially from the CD results, this adjustment slightly reduces induced drag and delays flow separation, further improving efficiency. From the calculations and tests, I applied a 3-degree washout at the wingtips, meaning the angle of attack at the tip is 3 degrees smaller than at the root. This washout reduces the risk of tip stall at high angles of attack while also weakening wingtip vortices, reducing induced drag, and improving the lift-to-drag ratio. Finally, regarding winglets, I made some comparisons. For low-speed Class 3 aircraft, induced drag is not particularly significant. The simulation results also show that the improvement is minimal, and adding winglets would increase engineering costs. By finalizing the main wing configuration, incidence angle, washout, and winglets, the theoretical performance is further improved, providing a solid basis for more detailed analysis. In the end, we test the dynamic stability. First, we determine the all-moving horizontal tail control angles that allow stable flight at different speeds. Using a 5-degree angle of attack as the baseline for stable flight, we tested the feasible rotation range of the tailplane. Within a range of 0 degrees to -40 degrees, the aircraft can maintain stable flight at speeds from 17.8 meters per second to 85 meters per second. Based on the previous calculations, we perform longitudinal and lateral stability analyses with both the main wing and the tail set at an incidence angle of 1 degree. Here, we use a pole map plotting the eigenvalues of the linearized aircraft dynamic equations on the complex plane. The horizontal axis represents the real part of the eigenvalues, indicating disturbance damping. The further to the left, the faster the damping. The vertical axis represents the imaginary part of the eigenvalues, which corresponds to oscillation frequency. The larger the absolute value, the faster the oscillation. Longitudinal stability, there are 2 modes. The short period mode corresponds to the pair of complex conjugate roots further to the left. Their real parts are small, meaning they have ample damping. The aircraft remains stable without excessive oscillations. At the same time, their large imaginary parts indicate that the aircraft responds quickly to control inputs. The long period mode is closer to the imaginary axis, but still on the left side, indicating that the aircraft maintains stability with a slow decay rate. In lateral stability, there are 3 modes. The one farthest to the left is the roll mode, a purely real root indicating ample roll damping. The mode closest to the center is the spiral mode, slightly to the left of the imaginary axis, showing weak spiral stability. At large bank angles, there is a very slight divergence tendency, but it can be corrected quickly with trim. The other pair of complex conjugate roots corresponds to the Dutch roll mode. Since their real parts are to the left of the imaginary axis and do not cross it, this indicates moderate damping and stable behavior. After the stability analysis, we'll move on to dynamic calculations for the aircraft in various flight attitudes, in order to determine and optimize the propulsion system. Thank you again for watching. If you're interested in the L'Avion Idéal channel, or if you'd like to follow Lyon's meticulous guidance, then don't hesitate. Subscribe to my channel.